Now let's tackle part 2, where we're going to get into the process of transforming the diffusion weighted signal into an ODF. And I want to teach you the differences in all the ODFs and some of the different models that are implemented at DIPY to do the diffusion ODF, the cue ball imaging, the analytical cue ball imaging, and this constant solid angle cue ball. So back to the math, we saw that we could integrate the radial part. So this is just another formulation that I showed you in the past slides to transform the diffusion propagator P of R into a diffusion ODF psi of theta phi. And we saw in the first part and in the demo that if we go in a region of the brain where the signal is aligned with the gradient direction, we tend to measure this donut that I showed you, right? So along the direction of axons, the actual diffusion signal is most attenuated in the orthogonal plane to it. And so this is a bit hard to grasp at first in diffusion imaging, but what you're interested in is maybe the direction of axons or how these axons are degenerating with disease, and actually the signal is maxed in the perpendicular plane, so at 90 degrees from it. And as you can see, the signal here and the signal here in the background is quite close. So this is challenging in terms of SNR and noise. And as you will learn this week, there are several ways to denoise and handle noise in DIPY. And so mathematically, I'm not going to focus a lot on the math, but there is a way to transform this donut into a shape that defines an ODF. ODF means orientation distribution function. What is the probability that I have diffusion along this direction? This is captured by the ODF in this direction. And so this Fonck-Radon transform, or another way, this was also introduced in the technique cue ball imaging, is the way to do this transformation. So what's happening? So you choose a direction, you find the orthogonal plane, and you compute the integral or the sum. So this is what this equation tells us. And that gives us a point on the ODF, this point. So you can see if my direction that I chose is not aligned with the underlying fiber population, the ODF that I get, the value of this integral, is not maximal. If on the other hand, I choose the direction exactly aligned with the fiber population and I redo this Fonck-Radon integral on the great circle, well, then this fits with the maximal value of the ODF. So David Tuck, in his famous cue ball imaging paper, showed that to the world, that it was possible to transform the diffusion weighted signal on the sphere using this radon transform. Why radon? Because it looks like computed tomography, which also does a radon transform, but now it's on the sphere. So that's why the Fonck-Radon comes into play. And so given a diffusion weighted signal here that we can extrapolate on a big sphere, we compute great circle integrals to get here diffusion ODFs. And this is the cue ball imaging technique and model. And it's very nice because it works for any fiber crossing population, whether you have 2, 3, 1 fiber population, without assuming you just do this for several directions. So you take a direction, you take the plane, you compute the orthogonal, and do this on and on and on and on, and it works. And so what David Tuck did in his famous paper is to do this numerically. So what I was illustrating with planes and integrals, he did this with a numerical solution. What I showed in my thesis is that we could do this analytically, just using the math and the beauty of the spherical harmonics basis. So it's possible, what usually we do is to take our diffusion signal, get the spherical harmonics coefficients, and compute the integral or the Fonck-Radon transform analytically to just get spherical harmonics coefficients of the ODF. So it's a three-step process. We load the signal on the sphere, we project the spherical harmonics, and then we transform the harmonics with an equation. So this equation is this one. You can read the paper. There's a nice proof to it. So it's just a simple math on the coefficients, right? So you get the signal, you get the C coefficients, and you apply 2 pi, the Legendre polynomial, evaluated at 0 for the specific order. And a little bit like magic, you get your solution. This just transforms the signal and performs this transformation analytically. And so you get your ODFs. And so compared with diffusion tensors that were known to be limited in crossing fibers where you get disks and very low FA regions, well, suddenly you start getting shapes of ODFs with crossing fibers. As we will see later, this is not perfect yet, but this was the first indication that yes, there were crossing fibers in the brain and that we could reconstruct them using a relatively simple algorithm. Limitation of cue ball imaging, well, these objects are quite fat and blobby. I call them potatoids here. So as you see in my code and my demo later, if we do not normalize the ODF, we get really blobby shapes. So just normalizing by min-max normalization here, you just subtract the min and divide by the ratio. You can see anatomy much better. You can see some of the crossing fibers showing up. But you see, you may get a feeling that we're not there yet, and we will get to spherical deconvolution later to really pimp this up. But lastly, it was noticed, not by me, but a few researchers, so Agaji, that the actual solution in David Tuck's paper and in my paper was lacking here the lambda squared term, or in my initial notation here, r squared. But if you add the r term here, you're adding a multi-shell dependency of the signal. You need data beyond a single b value. So this was done consciously because we wanted to do diffusion ODF and cue ball imaging from a single cue ball, right? The word cue ball comes from Q space and a single b value in Q space. But so to add this radial dependency now on the solution, you have to assume something about the radial decay of diffusion. And that's what constant solid angle ODF does. It assumes constant ADC in time. It assumes the mono-exponential decay of the ADC. And if you assume that, while you can actually solve the diffusion ODF with this r squared term in the equation. So this was done in parallel by Agaji and Tristan Vega to really basically give a bigger weight to diffusion signals that are further away in the propagator space. And if you do this, well, so this was the min-max normalized ODF, and now you can have the constant solid angle. So min-max normalization versus constant solid angle. So this is the CSA model, as you will see in my code. From the cue ball imaging and constant solid angle, it's now possible to extract a novel metric, the measure generalized FA. And it has this formula here that, again, we can extract from spherical harmonics. So it's the standard deviation on the sphere of the ODF divided by its root mean squared. So you can actually compute that on the sphere, but it's much more elegant and fast to actually solve this equation in the world of spherical harmonics. So it's just a difference between a perfect stick, which would be 1, and 0, which would be a perfect sphere. And this is a measure of how spherical is your ODF. So the analogy of FA in the DTI world, but now for the world of cue ball imaging and ODFs on the sphere. So now I'm going to switch to my demo, but we're going to stay in the same Jupyter notebook. So again, we saw how to simulate signal, and now I'm going to show you how to generate different ODFs here, diffusion ODFs, with some of the DIPY models. So I'm going to take over on my so now we're in the Jupyter notebook doing part 2 on ODFs. So first thing to note is, given a signal, so this comes from my signal above, you can generate the ground truth diffusion ODF. If you know you generated the signal with a tensor model, you can also generate the ground truth ODF. So we can generate this ground truth ODF. So this was it looks like for a 90-degree crossing. Again, you can play with the angles and single fiber versus crossing fibers, 2 3-way crossings above. So you see a very nice and sharp diffusion ODF from the ground truth multi-tensor model. Now we can declare a cue ball model. So again, we go get the cue ball model, and later we'll have this constant solid angle ODF model from the reconstruction. And this is classical DIPY simple code, where you declare the model with a certain gradient table and a spherical harmonic order. You fit the signal, and then you extract the ODF, or eventually the GFA. So super simple, 2 or 3 lines of code. So we run this, and as you can see, and as it fits with my notes or my presentation, this is a fat 90-degree crossing ODF that I'm not normalizing here. Right? This is the raw cue ball ODF, a potato. I can min-max normalize it. If I do min-max normalize it, I get something a little sharper, right? And in this case, the GFA is quite low, right? Around not even 0.1. So it has also the same limitations as FA, where in crossing fibers, the anisotropy, even though it's a generalized anisotropy, is closer to 1 than something that is anisotropic, because it is far from anisotropic. It's 2 modes of anisotropy. Now, if we move to the constant solid angle model, well, again, I get my constant solid angle for a specific order. In this case, I chose purposefully order 4 because it's a much noisier model. If you actually go to higher frequencies with order 6 and order 8, you have a lot of artifacts in the reconstruction, so I prefer to keep it low, because essentially in real life, all I would use this for, as you will see later, is to get my generalized FA. I would never do fiber tracking on this object. The real object for fiber tracking is using spherical deconvolution. But anyhow, we get our ODFs. You can see it's naturally much sharper. It's properly normalized as well. So if you actually compute the integral on the sphere, the results should be close to 1. And you can also min-max normalize it if you wish, just to increase the sharpness in a visualization. And you can see now the GFA is it's a bit higher. So in practice, essentially, I almost never use the cue ball, the standard cue ball model. I use this constant solid angle model to extract the generalized FA. Or I just use the Fonck-Radon transform to kind of have a feeling of what's in my signal, because it's probably the least, but the most model-free way to extract some notion of orientation in your voxel. All right, so this we can break here.